Everyone, and welcome to today's webinar on electrical safety testing circuit theory. And I am your host and presenter, Syed Abidi, one of the applications engineer at Associated Research, and I'm here live from Lake Forest, Illinois, 10 a.m. Central U.S. time. So a good evening to our attendees joining from Europe and other parts of the world. Let's take a quick look at our meeting today, our team today. We have Anthony Arroyo joining us as a panelist, who's also part of the applications engineering team, and Anthony will be assisting you guys on the Q&A chat line, and I highly encourage you to use that tool. We also have the organizer for today's webinar, Brittany Socha, who's also the marketing coordinator, and she's responsible for basically running the show here. A few quick notes on the webinar today. As always, we have a Q&A facility, and you can utilize that to ask any questions during the webinar, which Anthony will be more than happy to answer. Any questions related to running of the meeting, audio or visual issues, please address them to Brittany, and she will be able to assist you through the chat line. Also, like all our other webinars, this one is also being recorded, so the video slides and everything will be available, within a day on our website, which is arisafety.com/webinars. And if you would like to get a copy of this presentation, please contact Brittany at the following email address, brittany.socha@arisafety.com. Okay, so I think we have enough people or attendees with us so we can dive into the material. Here's a quick look at what we're going to be trying to cover today and learn today. We're going to do a quick review of all the electrical safety tests, which obviously we've already gone over these in the last webinar. If you were able to join us, great. If not, then we'll obviously do another review of all the electrical safety tests, and then we will try and learn about what each test does and what does the circuit look like, what's really going on in each test, and what part of the device under test is being tested. And at the same time, we're going to look at some circuits as well for each test type, and then we're going to use a major chunk of this webinar and the time to talk about some other features such as arc detection and Smart GFI. So I'm not going to go into too much detail right now. There's a lot of material towards the end for these two topics, and I know these are usually misunderstood, so we want to make sure that you guys understand and know how to use these features. So here's a list of all the common electrical safety tests that most of our instruments can perform, either in a one box or as standalone test instruments. The ground continuity test and the ground bond test, obviously meant for testing the ground circuit or the ground connection of any device under test, or any class 1 product, meaning that any product that has a ground circuit or a ground safety ground connection. So these first two tests are there to test that ground circuit. The next two tests, the dielectric withstand, also known as the high pot, and the insulation resistance, are tests meant to stress the insulation of a device. Now it could be any insulation barrier, the mains to chassis, or from any other point to any other point. And there's many different applications for a high pot test as well. And then the insulation resistance test is something very similar to the high pot test or the dielectric withstand test. So everything pretty much looks the same in terms of connections and everything. However, the results are a little different, and we'll go over that. And lastly, we're going to touch up on the touch current test or the leakage current test. And obviously, these, like I said, these have been covered in some detail in the past webinar, but we will try and review them as much as we can today. So with that said, I'm going to start with a poll question here, and we'd like to get some important information out of you guys. And our first poll question would be, what department in your company is responsible for ensuring that your electrical safety testing is being performed properly? So the poll is now open, and please take a minute to answer this question, and then we will continue.
Okay, Syed, we have our poll answers. What department in your company is responsible for ensuring that your electrical safety testing is performed properly? 28% said compliance, 8% said quality, 43% said engineering, 15% said production, and 8% said other. For those others, feel free to comment in the chat box. We love learning about your companies. Thanks, guys.
Okay, thank you, Brittany, for sharing the answers and the percentage. So it looks like it's kind of all over the place, but most of you went with engineering. So again, that means your engineering team is responsible for running what we call the type test, or the lab test that's during the design phase of the product, and then when you talk about compliance or quality, it's more at the end of production. So, okay, that's great information, and I appreciate you guys taking time to respond to this question. So let's continue with our material today. And the first test we're going to talk about is the ground continuity test and the ground bond test. And these two tests are very similar in that they are testing the same part of a of a device under test, which is the ground safety ground connection. The ground continuity test is a slightly less rigorous test, a very simple test to perform. All it's doing is just sending a small pulse, from either the ground pin of your device under test, and measuring that pulse back on the chassis of the device or any exposed metal that's grounded, and that's kind of verifying that a ground connection or a ground circuit exists and it's continuous. So that's all that this test is doing. And the test is typically performed under current levels of less than 1 amp, just to make sure the ground connection is continuous. And again, what's important to remember is that this test, as the name implies, ground continuity is only meant for devices that have a ground circuit. On the other hand, the ground bond test, which is performed in a similar fashion as the ground continuity test, it's a lot more rigorous test, meaning that this test basically verifies the integrity of the ground connection between exposed metal and ground wire of the power line or the line cord. This means that unlike the continuity test, which is only verifying that the ground connection is continuous, the ground bond test actually stresses the ground connection and passes a high amount of current through the ground circuit and measures the integrity of the ground circuit to see whether the ground circuit will work and protect the operator or whoever is operating the instrument, if in case there is a fault on the device under test, and or in the instrument itself, and if somebody's touching the chassis or the surface of the product, the operator doesn't get shocked, and the ground circuit should be able to take care of any fault currents and route that current back to the earth ground instead of through the operator. So the way this test is performed is, again, high current is injected into the ground pin of the product's power cord, and it flows through the chassis. It determines if the safety ground wire is capable of handling excessive current flow in case a fault occurs and the product's insulation fails. So let's look at the circuit for the ground bond test, and that's what we're going to focus on during this webinar. So the circuit for the ground bond test and the ground continuity test are very similar. In fact, exactly the same. It's only the signal that's injected into the ground circuit that differs and sets these two tests apart. So on the left side, you can look at it as the ground bond test instrument, and on the right side, we can assume this to be the device under test with a line cord, three-prong line cord, which is plugged into the ground bond tester, and high current is injected into the ground pin of this device under test, which flows through the chassis and is measured back on the chassis of the product using the 4-wire Kelvin connection. Now this 4-wire or the Kelvin return connection is used during a ground bond test to eliminate any inherent test lead resistance from the test results in order to give us a more accurate value of the actual resistance of the ground circuit. So the result of a ground bond test is a resistance measurement of the ground circuit itself. And obviously we know that current always likes to take the path of the least resistance, which means that the circuit of the resistance of the ground circuit or the ground wire should be very small. And if you look at the test standards, any UL, EN, or IEC standards, and if you look at if there's a ground bond test requirement in the standard, you will see that most of the test standards are asking for the ground resistance to be less than 100 milliohms or 0.1 ohms. So, further expanding on the circuit, this picture is showing us the actual path of the current. Now the current is injected again into the ground pin, and you can see the dashed green and black lines showing the path of the current, and it's measured back on the chassis. Now what really happens here? Well, when this high current is injected into the ground pin, and this high current can be of any value depending on the standard or the type of device you're testing. For our example, let's pick like maybe 20 amps of current we're injecting into our the ground pin of our device, and that current, when it flows through the circuit to the ground circuit, creates a voltage drop, and that voltage drop is then used to measure back the resistance, because we know when we inject this current, or when a ground bond tester injects current into the ground pin, there's also a voltage. Obviously you have to have some voltage to be able to inject that current, so that voltage level is usually less than 12 or 8 volts. So very low voltage and high current test, this one. And so as a result, the voltage drop occurs into the ground circuit, and that's used to calculate back the resistance of the ground circuit. And that resistance determines whether your device, the ground circuit of your device, is meeting the standard or whatever the requirement is by the standard, which is usually 100 milliohms for some types of products. For others it could be 200 milliohms, but really it's the test standard you want to look at for setting up the pass-fail criteria for this test. So here's a picture, here's this image showing a ground bond test failing, which means that what really happens here is, as a result of the high current flowing through the ground circuit, the voltage drop occurs, and the resistance measurement that was made is exceeding the failure settings or the failure threshold, which is in our case usually called the high limit or the max limit that you can program in the ground bond tester and any of the Associated Research ground bond testers to catch whether the resistance of the ground circuit is exceeding that value. And this way it will result in a failure, and you will know that you will have to look back at the ground circuit and see why it failed, or why is it high resistance, why is it not meeting. Maybe you need to take an offset reading to eliminate any test lead resistance, or just look at the ground wire itself and see why is it not passing the ground bond test or meeting the test standard criteria. So again, the ground bond test is obviously commonly considered a type test. However, we've seen a lot of our users of our equipment are performing ground bond tests in various industries as a production test, just to instead of a continuity test, they're doing a ground bond test just to verify and maintain top quality of their products. So the results are displayed in ohms. It's usually milliohms because it's a very small resistance value. And again, the ground conductor of a product must have a low enough impedance to handle any of that fault current that it's exposed to in case there is a fault that occurs. Some more information about the ground bond test. The test standards vary from standard, the test parameters vary from different standards. Manufacturers must consult the safety standards which they're trying to comply with before setting the test parameters. An example from IT equipment standard, the 60950, calls out for the test current to be twice the fuse rating of the product or twice the current rating of the circuit under test. So here it's giving you a criteria or a way to calculate what kind of current you want to use to test your product for a ground bond test. It's saying also talking about voltage, which is not to exceed 12 volts in this case, and the test duration to be 120 seconds. So again, the assumption is, when you perform a ground bond test and inject a high current through the ground circuit for a given period of time, and the ground circuit should be, if it's holding up that high amount of current for this period of time, we can assume that in its normal life cycle, the ground circuit will be sufficient to protect the user in case the operator gets shocked, or in case a fault occurs and high amounts of current flows on the chassis of the DUT, and the operator is touching the DUT, all the current will be routed through the ground circuit rather than the operator. So that's pretty much all we have for the ground bond tests, and let's shift focus a little bit and talk about the dielectric withstand test. Now, as we know, the first two tests that we talked about, the ground bond, ground continuity, are meant to test the ground circuit of the device. So any device that has a ground connection. Now, the dielectric withstand test and the next test that we're going to talk about, the insulation resistance test, which is also very, very similar to the dielectric withstand test. It's meant to stress the insulation or the dielectric, which in this case is the insulation of any device. So insulation, as we know, is what protects or separates current carrying conductors from the non-current carrying conductors. And almost all electronic products, or even non-electronic products, have some sort of insulation barrier separating different conducting paths. So this HiPod test is meant to, or is used to determine whether the insulation of a product is able to withstand an over voltage condition or a transient voltage condition for a given period of time without breaking down. So what that means is, basically, during a HiPod test, a high voltage or a high potential is applied between the mains input and any exposed dead metal. So, for example, if you think about a class 1 product with a line cord that has a line, neutral, and ground, the high voltage is applied by shorting the line and neutral together, and the return connection or the leakage current is measured on the ground or the chassis. And this determines how much current the insulation will allow to flow, and based on that measurement, the HiPod test can determine whether the insulation is good or needs to be looked at. So the result of a HiPod test is almost always a leakage current measurement, and that's because when any insulation is stressed with high voltage for a given period of time, some leakage current is going to try and flow through that insulation, and the quality of the insulation is determined based on how much leakage current it allows to flow through it. And again, insulation is another safety barrier as well for operators, because insulation is what does not allow current to flow, and it should have a high enough resistance to impede the flow of current. Now, the assumption behind the HiPod test is that if the insulation of a product, or any insulation in a product, is able to withstand a high amount of voltage for a given amount of time without breaking down, we can assume that during its normal life cycle, the product insulation will be sufficient and will be good, and it can be trusted in case some fault occurs in the device under test and there's leakage current or a current flowing on the chassis. The insulation will come good, and it will prevent high amounts of current from flowing on the surface of the product. And again, the leakage current is what determines the quality of the insulation. So in a high-pot test, the few of the test parameters that you have to look at are obviously the test voltage, which is always going to be a very high voltage, and we look at some examples later of the type of voltage that's usually used for high-pot tests. But a quick rule of thumb for a high-pot test is twice the voltage rating of your product plus 1,000 volts. So that means, for if you're running your mains to chassis high-pot test, you can, and if your product is rated at 120 volts, you can do twice of that, which is 240 plus 1,000. You can use 1,240 volts or 1.24 kV for performing a high-pot test. And this image on this slide is basically showing the circuit of the high-pot test. How does it look like, and what's really going on internally? And as you can see on the left side, we have our the safety compliance analyzer, Omnia 2 by Associated Research, and on the right side we have the device under test, which is basically a class 1 product that we're trying to show here, and high voltage is applied between the current carrying conductors and ground, and everything in the middle, which is the insulation, is stressed, and as a result a current flows, which is measured by the high-pot tester, and a pass-fail determination is made based on user input. So the good thing about the high-pot test is that it's not only a test to it's not only a test to determine whether the insulation is safe and it's good. It's also a quality test. A lot of engineers and people in the industry that use high-pot tests, they use it not only as a safety test but also as a quality check of their products, which means this test is also able to detect possible defects in the design of a product and workmanship, such as inadequate clearance distances between current carrying conductors and things of those sort. So here's a picture or an image of the circuit of the high-pot test. So on the top, if you can follow me here a little, you see the high voltage output is the little white connector, which is connected to the line and neutral of the device, which are the two current carrying conductors, and the return circuit is tied to the ground or the chassis, and high voltage is applied between these two, between the hot neutral and ground, and a leakage current determination is made. Here's an image showing the high-pot test failure. Now, a high-pot test failure can be of a few different types, meaning that there could be a complete breakdown, which means the insulation just could not withstand the high voltage that was applied across it, and it broke down, meaning that it allowed excessive amount of leakage current to flow on the chassis. So this is what one type of high-pot test failure. The other type of failures could be based on the user input or the failure threshold settings that any user would program in a high-pot tester. And most high-pot testers these days are programmable, user programmable, so you can go in and when you're programming or setting up your test, you can choose the voltage, you can set your current failure thresholds, meaning high limit, low limit, and to make sure that the leakage current measurement is falling between those upper and lower thresholds. If it does not fall within those thresholds, the high-pot test instrument will will detect a failure, and it'll tell you that something's not right because the leakage current range that you programmed is being either exceeded or it's falling below that range, which will result in a failure. So a few more things about the HiPod test. Again, before I continue, I want to let you guys know that the upcoming webinars for the 2017 series, we will be focusing. We have full webinars on ground bond, ground continuity, HiPod insulation resistance, and leakage current testing. So, if there's any detail on these tests that we're not talking about today, we'll definitely cover a lot more detail about these tests in the upcoming webinars. So stay tuned. All right, so we know that leakage current is present in almost every electronic device to some degree. Now, this leakage current becomes a problem when it reaches excessive levels due to dielectric breakdown or poor insulation, in other words. The result of a HiPod test is usually displayed in milliamps or microamps, depending on the test type. This means that a HiPod test could either be performed using an AC voltage or a DC voltage. Now, these requirements are always based on the test standard and the type of product under test. So, again, I would like to stress the fact that when you are looking at, performing HiPod tests or testing your products for safety testing, do refer to the test standard that you're trying to comply with. The other important thing about the HiPod test to know is that it's can be performed, or it is usually performed on both Class 1 and Class 2 devices, meaning that Class 1 device that has a ground circuit and Class 2 device that do not have any ground circuit, but they have a reinforced insulation or double or dual insulation. So we already looked at the test voltage and trip settings, and we also looked at the rule of thumb for setting the HiPod test. Now, here's a few important things that I want to get into, since this webinar is about the circuit, for each type of test. So here's something interesting that I want to discuss today, and this is what we call the failure detection. So this is basically, this diagram or this circuit is showing the different types of failures and other features that are part of the HiPod test that can be used as additional features, such as arc detection or Smart GFI, and some of the failure thresholds and or overload conditions. So what we're looking at here is that basically we're trying to show you what these different failures look like and what is the speed, how fast are these detected. So if you look at the first one, which is the arc detection, and again, we will talk about arc detection in a lot of detail later in this webinar. So the first one that we're looking at is arc detection, and this one is a high-speed detector. So if you have arc functionality turned on, or if your HiPod test instrument has arc detection feature, you can definitely use it to find out some extra details about the quality of the insulation. And this is a high-speed detector, so meaning that this would result in if there's an arcing event in your device under test, the test instrument, if it has arc detection turned on, will detect it very fast. The next in line is the leakage meter. Now, this is the meter settings that the user has programmed, which is like the high limit or the low limits for the leakage current. And that's a slightly slower detector compared to the arc detector. And then lastly, we have the overload conditions, which is also another high-speed detector. This means that when you perform a test, and if there's a breakdown or overload condition, meaning that the current leakage current reading or the measurement is beyond what the HiPod test transformer can supply, that's an overload condition, and that's also a fast detector. So again, this diagram or the circuit is just for our better understanding of the different types of events that are occurring during a HiPod test and that can be monitored. So with that said, let's again move on to the next test, which is the insulation resistance test. And we're not going to go into too much detail about the IR tests, and the reason is that this test is so similar to the DC HiPod test, and it stresses the same insulation on a product as the DC withstand test. The only difference between the the insulation resistance test and the high pot test is that the result or the measurement of the insulation resistance test is a resistance value rather than a leakage current. This means that the insulation resistance test is performed in exactly the same manner as the high pot test, meaning that high voltage is applied between the current carrying and the non-current carrying conductors, and a determination is made on the leakage current, but that leakage current, instead of being displayed as a result, is used up by the instrument to calculate back the resistance of the actual insulation of the device. So if you're performing an insulation resistance test, you will see the result will be a high resistance value. And this is why the insulation resistance test is basically not a very commonly used test. And even if you look at the most test standards that do specify performing a high pot test, you will see that there's no mention of insulation resistance test, and it's only used in very specialized applications, mostly for products that are repaired and are coming for repairs. The service guys might want to run an insulation resistance test to see if the insulation is still in good shape. And the way this test is performed, again, is very similar to the high pot test. And what we want to make sure is, and what the test standards are looking out of the insulation resistance test, is that the insulation of the product, the resistance of the insulation of your product, shall not fall below a certain value. Now, obviously, insulation, again, think about what insulation is. It's what's protecting or preventing leakage currents from flowing on the chassis of a device, and in doing so, it's protecting the user and by limiting the current flow. So we want the resistance of the insulation to be very high, unlike the ground circuit resistance that we talked about, which should be very low, so that the current takes the low resistance path. In this case, since we're talking about the insulation, we want the value to be very high, and the higher the the resistance of the insulation, the better it is. The more the quality of the insulation is good. So high insulation resistance value basically indicates good insulation. And again, the connections for, or the setup for the insulation resistance test is very similar to the high pot test. And the picture in the bottom, you can see the high voltage is the red wire showing the high voltage being applied on the hot and neutral and between the current carrying conductors and the ground. And the result is going to be a resistance reading. Quick example from one of the test standards, safety of machinery, EN 60204-1 specifies a 500 volt DC test between the power circuit conductors and protective bonding circuit, and the resistance shall not be less than 1 megaohm. So here you go. This test standard is actually telling you what voltage to use and how to set up the failure thresholds. Now in this case, you want to set up your insulation resistance test such that if the resistance measurement falls below the 1 megaohm number or value, the test should result in a failure. And most insulation resistance testers are programmable, and you can definitely set up the failure thresholds to catch any any type of failures that occur during the insulation resistance tests. So moving on, again, like I said, we're going to be covering all the test types real quick, and then we're going to dive into some of the other cool features of high pot tests that are available that you may or may not be using. So the next test that we're going to talk about is the line leakage, or the leakage current test. The term line leakage is also very commonly used, but the actual term, if you look at the test standards, is leakage current test. And the leakage current test is performed on electrical products to measure the leakage current which could flow through a person while the product is operating. Now this is a key word right here, while the product is operating. In the previous test types, the ground continuity, ground bond, high pot and the insulation resistance test that we talked about, the product is actually not powered on. We're just in the ground bond and the ground continuity. We're testing a dead product, product that's not powered on, and we're just testing the ground circuit of the product. And in the high pot and the insulation resistance test, again, the product is not powered on. We're just testing or stressing the insulation and taking leakage current or resistance measurements. The line leakage test differs from the other test types in that the device under test is actually powered on the way it should be, like either using an AC source or wall outlet, using its specified line line voltage, or in some cases 110% of rated input. And leakage current measurements are made while the device is powered on using a circuit which is known as the measuring device. And what this measuring device circuit is meant to do is to simulate human body impedance under different conditions. So obviously we don't want to perform a leakage current test on an actual human being, so we came up with the test standards have specified circuits that simulate human body impedance, that simulate how a human being may be exposed to different current values or current levels if touching different points of a product. So the measuring device circuit is used to simulate the human body impedance, and the test is performed under some fault conditions and normal conditions. So meaning that normal conditions just a device powered on and some leakage current measurements are being made, and some other fault conditions are things such as an open neutral condition or a reverse polarity, an open ground condition, and we look at that once we look at the circuit. And most common uses of leakage current tests are in the medical industry due to the strict regulations and the types of medical devices that there are out in the field. As we know, most medical devices make some kind of contact with the patient, like probes or clips or anything. So all those different points are tested during the leakage current test. Now the leakage current test is also required by some other standards other than medical, and obviously that's why we highly recommend looking at the test standard to see if your device needs to be to undergo a leakage current test. Now here's a typical circuit for leakage current test. Now what we're showing here is on the left side is the leakage current test instrument or analyzer. On the right side is the device under test. The device line cord plugs into the leakage current test instrument, and the device is powered up using the mains voltage. It could either be a built-in AC source in the leakage current tester or an external source. That really depends on your setup and your device under test. But what I'm trying to focus on more is the fault conditions and how they're simulated internally in the leakage current tester. So like I said, the leakage current tester is capable of simulating certain fault conditions. And if you pay attention to this diagram on the left side, you'll see 3 switches that are labeled S1, S2, and S3. And these switches or relays are what enable the leakage current tester to simulate fault conditions on the main input power of the device under test. For example, switch S1, if that opens, it's an open neutral condition. Switch S2, if it switches, that's a reverse polarity condition. And switch S3 is an open ground condition. And you can also see the little MD circuit at the bottom right of the picture, of the big picture. And that's the circuit that's actually used to make the leakage current measurements on different points of the device. Again, like I said, a lot more detail is coming up on these tests in the upcoming webinars, which are focused on each of these specific test types. So stay tuned in 2017. Here's a picture of the measuring device circuit for the medical standard 60601-1, the medical electrical equipment test standard. and this is the actual measuring device circuit that's specified in the test standard itself. So you know, if you're familiar with the test standards, if you've read through a few, you'll see that every test standard that specifies or calls out for a leakage current test also specifies the type of measuring device circuit to be used to make the current leakage current measurement. So this leads us to our quiz question instead of a poll question, and we just want to quiz you guys, you know, just to keep you engaged and see what you guys think. The question is, in order to help ensure operator safety, which of the following features would you utilize? And the poll is now open, so please take a minute to participate.
All right, Syed, our answers are in. In order to help ensure operator safety, which of the following features would you utilize? 24% said Arc Detect, 9% said High Limit, 52% said Smart GFI, 9% said ESD protection, and 6% said oven mitts.
Awesome.
Thanks everyone for participating.
All right, thanks a lot, Brittany, again for sharing the results of the poll. And to my surprise, the answers are all over the place. So, well, that's good. That's good to know, because again, the next few topics that we're going to talk about will clear up some of these answers that you guys gave for this quiz question. And the next few things that we're going to dive into are some of the extra features associated with high-pot test instruments. The first one we're going to talk about is the Smart GFI. Now, Smart GFI is basically a smart ground fault interrupt feature or circuit that's built into Associated Research high-pot test instruments. And this feature is mainly for operator protection. So, you know, based on the quiz question, those who answered Smart GFI, good job, and those who didn't, no problem. You learn what this feature is, and if you're not using it, you can now start using it once you know what it does and how it can protect the operator. So during a high-pot test, if you think about what really goes on, going back to the circuit diagram that we looked at, you know, when high voltage is applied across any insulation, so leakage current, you know, tries to flow through that insulation, and that leakage current is obviously coming out of the high-pot test instrument. So the Smart GFI circuit basically detects the current that's coming out of the high-pot test instrument, and is also at the same time detecting any current that's leaking to ground rather than returning back to the return connection. And in doing so, the Smart GFI, if it's enabled, if this feature is enabled in a high-pot test, it will detect whether there's leakage current flowing through ground instead of returning back to the high-pot tester. And the assumption is that if the leakage current that's coming out of the high-pot tester, the same amount is not returning back to the return connection and it's going to ground, there could be an operator who's standing at a ground potential and coming in contact accidentally, of course, with the high voltage line, and you know, some of that leakage current is flowing through the operator instead of the return connection. And this is where the Smart GFI, and the reason why it's smart is that it can detect, if it's enabled, it can detect whether a device under test is grounded or not. Normally, the return connection of you know, Associated Research high-pot test instruments are floating. So if it detects the device under test is grounded, it will it will automatically disable, because then we know that the device is already grounded, so there's no point in using the Smart GFI. It won't be effective. But if the device under test is not grounded, and the Smart GFI is turned on and it detects any leakage to ground, it will shut off the output. And the reason why it's shutting off the output is to protect the user, because the assumption behind the Smart GFI measuring any current that's not returning back to the return connection, the assumption is that that current is probably flowing through an operator, and this is a high speed shutdown circuit that disables the high voltage in less than 1 millisecond. So, and this is how it protects the user. And again, it is an active circuit which monitors the configuration of the return connection and automatically sets itself accordingly. Now again, remember that this is more geared towards protecting the operator, but what we have seen is that the Smart GFI also comes into use in determining whether a product is leaking to ground or not. If a product is somehow it's not grounded, but we think it's not grounded, and we're testing it, and the Smart GFI is enabled in the HiPod tester and keeps tripping when you perform the HiPod test. It keeps failing for Smart GFI. Well, there's something somewhere in the device under test that's leaking to ground, and that gives us something to look for on the device under test. So here's a circuit. Here's what the circuit looks like for the Smart GFI. As you can see, the assumption here is that if any operator comes in contact with the high voltage line or the output, and the operator is standing at ground potential, the leakage current will try to flow through the operator because it's finding an easy path towards ground rather than the impedance of the transformer through the return circuit. And this is where the ground fault current sensor comes into play and determines and detects if there is any leakage to ground, and it basically shuts the output, assuming that somebody may be getting shocked. So with that said, I'd like to kind of show you guys a quick video that I made for the Smart GFI feature. And what's going on here is that I'm just going to pause it here and show you that we have a little 1 k ohm resistor, and which is again connected back to earth ground, and we have a AC withstand test set up to be performed, and the voltage output is going to connect to the one end of the resistor, which is grounded, and you will see that the Smart GFI circuit, the result will show a ground fault. So basically, this is what the assumption behind the ground fault circuit is, that if it detects anything leaking to ground rather than returning back to the return connection, it will result in a ground fault, which is on the screen denoted by GND FLT, which basically is short for ground fault. So that's again, the ground fault is a feature available on most of our Associated Research HiPod test instruments, and it is a user programmable feature, meaning that the user can actually program the current level anywhere from 0 to 500 or 5 milliamps. And again, the Smart GFI will trip based on that user setting. If it detects that much current flowing through ground or not returning through the return path, the circuit with the Smart GFI will result in a failure. Again, this will be different from the HiPod test failure. So make sure you understand the difference between a HiPod failure breakdown versus a Smart GFI, because this is more of a user protection circuit, and it doesn't tell much about the device under test, rather than that it may be leaking to ground. So the other feature that we're going to talk about, and I know we're nearing the end, so the other feature that we're going to talk about, and this is again a part of the HiPod test, is the arc detection circuit, or the arc detection feature. Arcing is basically a momentary partial discharge due to the intense concentration of high voltage electric field across a dielectric when a high voltage is applied across or through that dielectric, just like it is during a HiPod test. So the arc detection is just another extra feature built within the HiPod test itself that you can either turn on or leave it off. If most test standards do not require looking for arcing. Again, this is an extra feature that we have built into our HiPod test instruments to give the user a little bit more information about the quality of the insulation, and maybe in some cases I've seen people use the arc detection feature to kind of predict how the insulation is going to behave in the next few maybe months or years. So it just gives us some extra bit of information, and an arc detection failure really doesn't mean that it's a HiPod failure or the insulation has failed. It's just a momentary partial discharge, so that doesn't mean that the insulation is totally bad and needs to be replaced. It's just an extra added feature. So in HiPod testing, the dielectric, as we know, is the insulation of the device under test. Arcing produces momentary spikes in nominal leakage current waveform, and again, it's different from the dielectric breakdown, doesn't necessarily mean HiPod failure, and it just provides useful information about the product's insulation. And here's what what we're trying to explain here is that arcing is a momentary partial discharge, meaning that these high frequency signals riding on the main waveform are detected. If this is detected, and arc detection will detect this the signal and result in an arc failure. So here's how arc detection works. Those high frequency signals are passed through a high pass filter, and once they're passed through a filter, they're fed into a comparator circuit, and that comparator circuit compares those current levels with the user specified setting or sensitivity level, and it's usually from 1 to 9, and the comparator compares the input from the user versus what's actually being detected, and if the readings match, it results in a arc detect, or actually an arc failure. And it's a fast interrupt. It could be as fast as 400 microseconds, or even faster than that in some cases. It really depends on the CPU. Here's a table showing the arc setting. This is what the user can actually input or program within the HiPod test for arc detection. And again, what's important here to remember is that arc detection is not an exact science. It is dependent on a bunch of variables, and that could be the surface geometry, the altitude, atmospheric pressure, humidity, and a lot of environmental factors determine or impact arc detection circuitry. So this table and the values based on the arc setting versus the current trip level are approximations. So these, again, I would use them, but I wouldn't rely on them 100%, because again, we know that arc detection is not an exact science, and it will be affected by a bunch of different environmental conditions or variables. And again, arc detection is usually present in most of associated research HiPod test instruments as an extra feature. You can, if you're not required to look for arcs, you don't have to use it. You can just turn it off, and it will never result in an arc failure. So what I do want to show you guys is a quick video on arc detection that I recorded. And you will notice in this video that we're actually setting up an arcing event by using an arc detection apparatus, but using two metal balls spaced very closely and applying voltage through a resistor on one side and between these two balls. Now, the first time when we ran this test, there was arcing, and it did not catch an arc failure because arc detection was off. Now we're turning the arc detection on and setting a sensitivity level, and as soon as we hit the test button, you hear that little arc, and the test results in an arc failure. Now, this basically means that like I said, our HiPod test instruments, made by Associated Research, are built. They have a built-in arc detection feature, which is user adjustable, and the user can either turn it on or off if they want to use it or don't want to use it. But if they, based on this video, you can see that what we did was we applied high voltage, across these two metal balls, and there was an arcing event. They're spaced just closely enough to create an arcing condition, and as soon as the arc detection feature was enabled and the arc sensitivity level set to 5, which is the middle in that table that we looked at, the arc detection circuit resulted in a failure. It caught an arcing event, and that's what the arc detection feature does, is it catches any arcing event. And these arcing events, in some cases, are common for certain type of devices or products. We had a customer who was who was getting arc failures, and they were testing PCBs. And obviously in PCB design, if there's if the spacing of conductors is sometimes too close, or if there's a small air gap between two conductors, the application of high voltage during a high-pot test can result in arcing events, and these events, can cause problems or can raise questions regarding the quality of the insulation. So as a design engineer, you might want to use this feature and see if there are any arcing events going on in your product during the high-pot test. So that kind of leads us to the end of our webinar today, and hopefully the information that we provided was useful and you did learn something out of it. And again, our next webinar is on the high-pot test, and as I mentioned, the next few webinars that we're going to be doing in 2017 will focus purely on each of the test types that we kind of touched upon today. So if you want to learn everything there is to learn about the high-pot test, join us on Wednesday, May 17th at 10 a.m. U.S. Central Time, and we will make you guys high-pot experts.
Hey, Syed?
Yeah.
So going back to the question and answer slide, we actually did have a good question from Justin referring to line leakage testing. He wanted to know a little bit more about the measuring device. His exact question was, is the MD usually a programmable part of the safety instrument, or does it need to be built into a test fixture that interfaces between the safety instrument and the DUT?
Okay, so, thank you. All right, great question, Justin, and I'm glad you asked it. Again, like I said, we'll go into more details once we go into the leakage current test webinar in the coming days. But for your question, the measuring device circuit is an actual physical circuit that, in our case, if you look at the Associated Research leakage current testers, these circuits are actually built in as physical circuits in the instrument. And we have up to, if I'm not wrong, 7 to 8 different measuring device circuits based on different test standards. We have one for 60950, we have one for 60335, 60601 medical standard. So these are actually built in form of an actual circuit. And there's also room, if you cannot find a measuring device circuit that you are trying to use that's built into the instrument, you have a different type of requirement, and your measuring device circuit is not one of the built-in MD circuits in our device. There's always room and a connection for building your own little MD circuit and tying it with our leakage current testers to be used as a measuring device circuit. So at this time, we were going to leave some time open for questions. Anything that comes up on the chat line, Tony will basically call out the question. I'll be more than happy to answer. In the meanwhile, I want to go over some ending material here, such as resources. All our webinars are obviously stored on our website. You can access them along with a lot of other educational materials, such as white papers, application notes, quick start videos, quick start guides, standard guides, and a lot of good info on our website. So I highly encourage you to keep checking our website for educational information. And I also want to throw this one out there. We have an applications consulting program that we just started, and obviously there's a lot of detail to it, which you can learn more about if you visit our consulting page on our website. And basically, just to quickly go over what we offer, we can help our customers overcome challenges and mitigate risk on the production line and the lab by coming out to your facility, training you on using our instruments, how to best use our instruments, how to set up safe workstations. We can do the safety standard analysis for you to determine what type of tests you are required to perform and how to best, how to perform them in the most safe manner, and which is the most suitable test instrument for you. We can help you with all that, and we can also help you with your qualification or validation procedures, especially for our medical customers who I know have to perform an IQ, OQ qualification procedure. We have some documents, we have the knowledge and the personnel who can actually help our customers, achieve all of that and make their auditors happy. So again, if you would like a copy of this presentation, please email Brittany Socha at brittany.socha@arisafety.com. Check out our website, arisafety.com. Our next webinar, again, I think we have already gone over that, May 17th. And at this time, I would like to thank you all for taking out time wherever you are and for joining us. And hopefully you learned something good out of this. And we expect you to join us for our upcoming webinars, which are, again, we're going to be providing a lot of good information. Once again, this is your host, Syed Abidi, live from Lake Forest, signing off. And also a big thank to Anthony Arroyo for being the panelist, answering chat line questions, and Brittany for running the show smoothly. Have a great day.